In my last few videos, I've gone over how to find critical numbers and using those to find maximum and minimum values in a function, as well as inflection points and intervals of concavity. Well, in this video, I wanted to show you how to put all those things together so that you can get a complete picture of what a function looks like so that you can sketch a graph of it. And this actually was one of the problems that I talked about in my weekly live stream last week, which I'm doing every Monday night at 5 Pacific, 8 Eastern. And I think you'll find it pretty helpful. So be sure to stick around to the end of the video. And without further ado, let's go ahead and jump on into the problem. So we're going to find the local max and min values of this function. We're going to find intervals of increasing and decreasing and intervals of concavity and inflection points. So we're basically putting together kind of all the stuff that we've been talking about so far. And we're going to use all this information to sketch a graph of what this curve looks like. Let's go ahead and, we're going to start pretty much just by taking the derivative. That's going to generally be how all these problems start, where we're asked to find the intervals of increasing, decreasing, the critical numbers, the inflection points, all that kind of stuff. So first of all, we just need to find the derivative of our function here. So the derivative of this function, we can just kind of take it term by term here. Derivative of 2 is 0, so that's not going to do anything. Derivative of 3x is going to be 3. And then the derivative of negative x cubed, we can find using the power rule. So we're gonna again have negative, bring our 3 down in front, leave our x as x, and then lower our power by 1. So it's going to be negative 3x squared. So this is our derivative. So if we wanted to then find our critical numbers, we would take our derivative and set it equal to 0 and solve for x. So solving this for x, we can add 3x squared over to the other side, divide both sides by 3, and then take the square root of both sides to cancel out the squared. So that gives us x equals, and this is so one thing you want to be careful of. When you take the square root of both sides of an equation like this, you need to take the positive and negative square root. So we actually have two different critical numbers here. X equals positive and negative square root of 1, which is just positive and negative 1. So in other words, we have x equals 1 and x equals negative 1 as our critical numbers. So now we can do the first or second derivative tests. And again, those are on my study guide if you want to go grab those. But I prefer the first derivative test. I think it's a little bit easier just because it requires finding one less derivative. But in this case, we're going to have to find information about inflection points and concavity. So we're going to need to find that eventually anyway. So if you wanted to do the second derivative test, this would be, a good chance to try that out. But again, first derivative test, we're just going to draw our number line, put our critical numbers on there, and plug in some number that's in each of these 3 intervals. We split our number line up into 3 parts basically by having these 2 critical numbers here. So we'll plug in, let's say, -2, 0, and +2. So if we plug in -2 into our derivative, so into this right here, we're going to get 3 minus 3 times -2 squared is 4, +4. So that gives us 3 minus 12, so -9. So our derivative is negative when x is -2. So that tells us that our slope is negative and that our function is decreasing over here. Okay. Then if we plug in x equals 0, we're going to get 3 minus 0, which is 3, which is a positive number. So that tells us that our slope is positive, which means that our function is increasing in this interval. And then if we plug in 2 into our derivative here, we're going to get 2 squared, which is 4, times -3 would be -12. So 3 minus 12 again, which is again -9. So our derivative is negative, which means that the slope of our original function is negative, which means that our function is decreasing over here. So we can see that we have a critical number, or a critical point basically, at x equals -1 and at x equals 1. And that x equals -1 is going to be a minimum because we're decreasing to the left, increasing to the right. X equals positive 1 is going to be a maximum because we're increasing to the left and decreasing to the right. Okay, so now what we need to figure out is exactly where our inflection points are, because what that is going to be able to tell us is our intervals of concavity. So basically what we're going to be able to figure out is exactly when this function switches from concave up to concave down, somewhere between -1 and 1, presumably, but we can figure out exactly where that is. So to find our inflection points, we're going to take our second derivative and set that equal to 0. So if our first derivative is here, f prime equals 3 minus 3x squared, our second derivative is going to be f double prime of x, which is the derivative of our derivative. So the derivative of this here, derivative of 3 is 0. And then the derivative of negative 3x squared, again, is just going to be power rule. So we can bring our 2 down in front. Negative 3 times 2 is negative 6. Keep our x as x, and then lower our power by 1. 2 minus 1 is 1. So it's just negative 6x. So then again, to find our inflection points, it's just like finding our critical numbers, but we do it with our second derivative instead of our first derivative. So we're going to take our second derivative of negative 6x and set it equal to 0. Well, it looks like there's just going to be one inflection point here. If we divide both sides by negative 6, we're going to get x equals 0. So we have one single inflection point at x equals 0. So what that tells us is our function is going to either switch from concave up to concave down, or vice versa at x equals 0. Well, to figure out which it is, we can do the same kind of thing that we did up here with our first derivative test. We can basically draw a number line, put our single inflection point on that number line. Now, do keep in mind, a lot of people do make this mistake of specifically putting 0 on this number line all the time. You only want to put 0 on your number line if it is your inflection point when you're testing intervals of concavity, or if it is a critical number when you're testing intervals of increasing and decreasing. Notice up here, 0 was not a critical number, and so we did not put it on our number line. It was in between two of the numbers that we had on our number line, so we did plug it into our derivative, but we did not put 0 on the number line. Just be careful of that you're just putting your inflection points or critical numbers on your number line. So now to figure out if our function is concave up or concave down on each of these intervals from 0 to -infinity and then 0 to +infinity, what we would do is just take some number within this interval. So let's just say -1 and +1 and plug that into our second derivative. So if we plug -1 into our second derivative here, we're going to get -6 times -1, which is +6. So a positive number in the second derivative tells us that our function is concave up here. Remember, our second derivative always tells us about concavity, where our first derivative always tells us about slope of our original function. Okay. And then if we plug in x equals 1 here, we're going to get -6 times 1 times +1, which is -6, which is a negative number. So that means our function is concave down here. So basically our function, it's going to be decreasing from -infinity to -1, increasing from -1 to 1, decreasing from 1 to infinity. And the point where it switches from curving upward to curving downward is right at x equals 0. So if we now want to kind of sketch a graph of this function, we could kind of combine the information we gathered about our slope plus the information we gathered about our concavity. And we know that our function is going to be something, well, let's just worry about the horizontal axis for now. Something like this, where we have a minimum at x equals -1. It's going to be concave up until we get to x equals 0. And then right at x equals 0, so right above here, it's going to stop curving upward and start curving back down. And then we're going to have our maximum, our local max at x equals 1. And then it's going to keep coming back down here. So what we could figure out if we wanted to is also exactly where these points, these max and min values are. If we wanted to do that, all we would have to do is take x equals -1 and x equals 1 and plug them back into our original function. So if we figured out f of -1, that would just be plugging in -1 in for x here. So we would get -1 cubed well, let's just write out how we would do that here. So -1 cubed is -1, but there's a negative here, so we're actually going to get +1 there. 3 times -1 is -3, and then 2. So 2 minus 3 is -1, plus 1 is 0. So at x equals -1, we're right on the x-axis actually. So in reality, our x-axis would be right here, going through this point here. And then our y-axis would come up here like this. Here's x equals -1. Here's x equals 1. We could figure out exactly how high this point is by simply plugging in x equals 1 into our function. So instead of -1 here, we would do f of 1, which would be 2 plus 3 times 1 minus 1 cubed, which would just be 2 plus 3 is 5, minus 1 is 4. So this maximum here would occur at y equals 4. And now this gives us a pretty good idea, or a pretty good sketch of what our function f of x is going to look like. Something like that. Well, I hope you found this video helpful. If you did, please be sure to hit that like button down below. And this video did use a few of the concepts discussed in my free Calculus 1 study guide, so be sure to check that out. There's a link down in the description below. And if you want to keep learning about intervals of increasing and decreasing of a function, or intervals of concavity, I have made a few other videos on those, so be sure to check those out right over there. Thanks, and see you next time.